Good afternoon. Let's get started. So please sit down. It's a pleasure for me to introduce our second keynote speaker in this year's LCN. The second keynote will be given by Dr. Muriel Médard. I think many of you know her, but I'll do a quick introduction. So she's a professor for engineering and computer science at MIT. She's, I think, very famous about network coding, so she's done a lot of work on this. She leads the network coding and reliable communications group. She has founded 2 companies to commercialize network coding. She's an IEEE fellow. She's the editor-in-chief of the IEEE Journal on Selected Areas in Communication. She was the president of the IEEE Information Theory Society in 2012. And she was on the board of governors there for more than 10 years, if I read it correctly. And I could go on and on. She has done many keynotes, best paper awards, and so on. But I think I'll stop now and we'll go into the details and technical details. So welcome, and we're looking forward to your keynote.
Thank you. Thanks for the kind introduction, Neil, and thanks also not just to Neil, but everybody on the organizing committee for inviting me. So stormy clouds, the name I didn't know would be so adequate given the weather that was chosen before the weather report. When trying to figure out what kind of talk to give, as a plenary, one always has the temptation to do something very safe, that's to say maybe an overview, semi-tutorial of an area, maybe one is very active in, such as network coding. Or the other temptation is, particularly with a concept such as this, to try to present some things which are maybe more incipient, and hope that there will be a discussion, a reaction, and that this will generate interest, particularly from your work. So I went with the latter, and that means that many of the results we're going to show are quite recent. It doesn't mean that they're not polished, but it does mean that the consequences and what this means, in particular for the practice of networking, is not clear to me. And I hope to convince you that there's some beguiling possibilities, and maybe also to convince you to investigate those possibilities. I shall not do a good job at saying who did what work. These are my main collaborators in this area. Actually, my student just graduated, just graduated, and since postdoc in ICANN, he's going to start faculty position at Harvard, so he has a lot more affiliations. Let me just jump straight in. So, we're talking about security, and we start with Alice, Bob, and Eve. Who else? So Alice, as usual, wishes to speak to Bob, and we're going to use very information theoretic notation, so forgive me, but it's just out of habit, where Alice wants to send a message, which we affectionately call X. And she wishes to send this message to her friend Bob, and Eve, the eavesdropper, wishes to recover the message. So of course, if Eve can see X perfectly, then Eve would know exactly what Alice wanted to send. So what we're going to do is we're going to add another layer. We're going to allow Alice and Bob to share a key. And this key, which we call K, is going to allow Alice to encode in some way, modify X, so that Eve will see not X, but some function parameterized by the key K of X. Bob, having been given the key K, is able to invert this function, this parametric function of X. And the hope is that Eve should know as little as possible about the message. Okay, so here's a cartoon version of security. I just don't want to know a whole lot. And the way we describe often that Eve doesn't know a whole lot is that the mutual information between X and Y is less than something small, which in the usual way we make acid. Okay, so that's our goal. It seems like the same goal that we've been pursuing for many decades. It's a very reasonable goal, but there are many questions that we can ask. So first of all, what does it mean to learn as little as possible? If you're talking from an information theoretic point of view, it doesn't necessarily mean that it's just computationally hard. Indeed, if you look at for coding, particularly coding for communication, we do things that are incomplete all the time while standing on our head. Basically, you look at something like a little density character check code, you don't actually know when it's going to finish. You really don't. You just let it fly, and it just does. And it does at 10 gigabits per second on a chip. So, you know, the notion of complexity is not lost, but somehow it's not necessarily one that we know how to incorporate, rather. So the question that I'm asking here is, how do we define this cipher, this F of K? And the other one is, what are the fundamental performance limits, where, as I mentioned before, we're basically going to throw complexity to the dogs. And let me tell you right now, we're going to throw complexity to the dogs. Actually, I had a question at lunch. Somebody asked me, are you going to talk about crypto? And I said no, and I'm now saying no-ish. Okay, you kind of know. Of course, if you look at the beginnings of information theory, and by the way, next fiscal year is going to be the 100th anniversary of Shannon's birth. You look at the mathematical theory of cryptography that came out right after the paper in 1948 that really established capacity. Out of that sort of came two different strands. One of them, which we would recognize as more computer science oriented, the other one being more information theory oriented. Of course, this is a cartoon. There's a huge amount of overlap, and I'll talk about it in a little bit. And, you know, if you look at some sort of epitome of this computer science approach, you see the Helmut, you know, in the 70s, which, by the way, was a paper that was recognized by the Information Theory Society, or the Information Theory Society, as before. So at the time, it was still seen as being part of information theory. And it, again, in the most, you know, crassly simplistic way, looking at the complexity of some hardness assumptions, the adversary's computation bounded. And again, it's something that has done extremely well. Right? I mean, we don't need to argue about how successful this view has been. It has done very, very well. And then we have another view, which is more an information theoretic view. And again, I'm just taking one example and holding it out as sort of a representative, an earnest of everything else in that field, which is, for instance, the wiretap channel. So there's error relate on a wire. And the idea here is an idea that you can have, in some cases, perfect secrecy, which we'll go over in a minute what that is, or in other cases, less than perfect secrecy, which we'll also define what that is. But it has no computational assumptions. And again, when you think of an area where we do things such as decoding, having no idea when it's driven to the end all the time at very high bit rates, it's not necessarily that we're really dismissing it, it's that in some cases we simply have encountered the fact that we can deal with it. Okay? So, based on this, there's been a lot of work, as I said, in the intersection, in effect, among cryptography, coding theory, and information theoretic security. And this is what I would like to talk about in the first half of my talk. And as I said, you know, there's a huge literature. I'm just giving a few examples. We talked about the Helmut. We talked about Reiner. There's been a huge amount of work, recognizably at the intersection of cryptography and coding here. For instance, McLeese, you know, things that the McLeese crypto system, right, which is really a coding-based crypto system, which has been shown to be secure even, you know, on the quantum attacks and so on. So, you know, this is a very rich area that's constantly evolving. I just want to call out a little bit some of the recent developments, particularly, you know, starting at the end of last decade, going very strongly to this decade, of course, my book and others. Looking at the issue of information theoretic security for wireless channels. And one of the reasons I want to bring that up is because we're going to revisit, in the second part of the talk, one of the core assumptions there. Okay, maybe uncomfortably, certainly for me at the beginning when I saw this. Okay? Because we're going to see that there may not be any complexity assumptions, but there are other assumptions that also render this whole area, you know, somehow difficult to get. Okay, so what's the motivation? Why look at it now? People have been looking at these things, as I said, successfully in different portions of the intersection for a while. Well, I think to some extent, and very much akin to the ones that I'm going to be showing here. You have to manage security and metrics, particularly as you look at systems which are more distributed, which are tending towards peered systems, not necessarily because it's it's just an ad hoc peering, but because it's designed to be a peered system for a variety of reasons. And at the same time, as I said, there's been work starting towards the end of the last decade, usually concerned with looking at the mutual information between this X that Alice sends and this Y that we receive, and usually having some vector X dimension N, and then some Y which is somehow generally smaller, right, where R is less than 1, but not always. Okay, and that's been the logical example. And out of all this, the question, if you recall, that we're trying to figure out is what happens when I simply want to mitigate the leakage of information. What can I say? All right. And what I'm going to introduce here is a recent development that we worked on, and also I'm going to try to connect it, as I said, to some of the developments that I see or that I've been working on separately in the area of distributed storage. One of them I'm going to introduce this notion of list source code. Many of you have heard of list decoding. Started out with Elias, was probably reinvigorated significantly by Stormy and Sudan in the early 2000s by looking at practical construction of list decoders and list decoders. So here we're going to look at list decoding, but from a compression side, and I hope it make it clear as the topic evolves. And from this, I'm also going to join it with a new method which we're calling symbol secrecy, which is what can an adversary learn. And in particular, what can an adversary learn without any of the constraints on complexity, which we have decided not to take. And finally, then, and this is what's going to relate us to a more systems-based consideration, is can I construct codes that somehow are able to achieve optimality in a sense which we'll define later in terms of symbol secrecy. Okay, so let's go back to our friend Alice Barker. All right. So the standard approach is what I would like to have is perfect secrecy. What perfect secrecy would mean is when I exchange this key, the mutual information between X and Y in the absence of the key is 0. That is to say that E simply cannot obtain any information whatsoever. Right? That's the one-time pad of Shannon. That's it, I can't figure out anything at all. And the problem with this is that H, where H is a Shannon entropy, and we'll go in the second part of the talk, we'll revisit this notion of entropy. But basically, it's the same entropy that, either you covered in information theory class or you covered in, your thermodynamics class. It's, minus P log P, where P is the probability of the random variable. And the sum of all minus P log P, so that's a Shannon entropy. In that case, the entropy of the source has to be equal to the entropy of the key. Roughly speaking, the binary source, it means that my binary key has to be the same length as the source. So, in order to hide something, I have to generate as much randomness as that which I'm trying to hide. So it's really expensive, fine honors. All right? So, in general, that's not what we do. We generally have keys which are smaller. Okay? So generally, we have keys where the entropy of the key is much, much smaller. So if I tell you that I'm using a crypto system with law-length key, I assume that the key size is the same, and I use it whether I have a big file or a small file, and only need to renew my key every so often. Okay, so that the entropy of this key X is much, much smaller, and in that case, we know that we cannot get to the perfect secrecy. We know, in effect, that I can only get to a small region of information. Question is, can I still make some sort of fundamental security? All right, so let's see the insights from the one-time path. The insight from the one-time path is the following. I had a source of n symbols, and I had a key of n symbols. symbols, and I sum them up. Think that if this is, the summation is an XOR, I was dealing with bits, key, and the source, and that became my Y. And the reason this thing is secure is because if I look at any possible element of my ciphertext, its pre-image, its possible set of pre-images is a set of all the messages. There is a key that will give me any pre-image in that set of messages. So the thing is completely spread out. I look at the output, and I still can't make up my mind which message is sent. I don't know anything because this pre-image is very simple. Okay, the problem is that the size of the pre-image may be limited in general if my key is going to be small. Okay, so I'm not going to be able to have the pre-image in my ciphertext be the entire set. So the question is, why don't I create a system, a code, in such a way that given that the size of my pre-image is limited, I can only do so much in terms of that size of pre-image. I somehow design the pre-image as well as possible. And that's what this source code does. So this source code is going to take n symbols. It's going to map it to nr symbols, where my r is between 0 and 1, in the case where I was dealing with ones I had always 1, they would be the same size. Okay? And for any element in the ciphertext, I'm going to have a set of pre-images, and think that my key length was k. I would assume that I have 2 to the k pre-images if I had k bits for my key. Those are the possibilities. And this is to say that, if I had all the time in the world and I don't care about complexity, I would write down by hand every 2 to the k possible keys, and then I would figure out for each of those keys what the pre-image was. That's it. And of course, what I would want is I would want the pre-image then to have some desirable properties. In particular, I don't want it to preserve any sort of features, right? I want that pre-image to be as spread out as possible so that being in that pre-image really doesn't tell me anything about the elements in that pre-image. Because I want the elements in the pre-image to be as spread out as possible. So here, it looks like they're bunched up, but they're not bunched up by any sort of similarity. I just want to make sure that there is no similarity. That, for instance, I cannot say something that I say the husband distance in terms of bits between these different pre-images. And of course, in order to decode, what I have to provide the legitimate receiver is some auxiliary information which allows the legitimate receiver in that pre-image to identify which particular element was the correct one, the one that was encoded. Okay, so that's the advantage that the legitimate receiver has over the eavesdropper. So it has enough to resolve the list. That auxiliary information is going to be related to the key. Right? Okay. So as I said, the size of the pre-image, at least in the logarithm, can be equal to the key, and it's going to be dependent on the encryption. The nice thing about this is that this subsumes deterministic encryption. Right? Any deterministic encryption where I give you just exactly the k bits for my key maps to this. Again, if I don't consider complexity, I just write everything out. That's the pre-image. It also subsumes a one-type pattern. The one-type pattern just so happens that that dark oval happens to be the entire loop, the entire set of messages. All right. So how do I create some sort of continuity between a deterministic key, where my key size is always the same, it's always a particular number, I have 120 bits or whatever I have, and something that goes all the way to the one-time pattern. So what we're going to do is, I look at a notion that we call symbol secrecy. So again, this R here is between 0 and 1. I have my input string. I'm mapping it via F, which is parameterized on the secret K. And the question that I'm going to ask is, what can you learn about individual symbols, whether it be the first symbol or any subset of symbols? And the way we're going to determine this symbol secrecy is that we're going to consider mu properties which I haven't defined properly mathematically, but we can get to it very easily that I wish we had. And it turns out that there is a fundamental bound, and we'll show later how to get to that. And this fundamental bound is that if you give me whatever the level of secrecy is, which we're sort of encapsulating in this abstract, and I look at a discrete memberless source to say something renewably, okay, I can achieve a simple secrecy which basically goes between the entropy of X and something, sorry, I can achieve a secrecy that goes between 0 and the entropy of X over the size of the initial set of messages. So this is, normalized according to the size of my outlet. Okay? And it's just a line. It's just a line. And basically what we would say is, if I add one more bit of secret, I shorten by 1 bit what I share with E. So there's basically just a nice linear relation between which bits you're putting on the secret side and which bits you're putting on the side that's revealed to E. But it's done in such a way that no particular bit is ever, of your initial message, is ever revealed per se, because I'm spreading it out with this simple secret. Okay? And that's why it's in this source code, because basically I'm source coding, I'm compressing. But I'm compressing down to a list, which Eve can reconstruct that list, and then the resolution of the list comes separate. So it makes sense. I have a number of bits, and I could put all of them to be secret, but then I'm back to the one I had. Or I could put none of them to be secret, everything's in the clear. I could just put a given number to be secret, that's your traditional key. All right. So now that we've established this, we know that when I design for a secrecy scheme, I should be able to look for a higher simple secrecy. And now the question that you're asking is like, okay, I understand that you have this idea of allocating bits between the secret part and the non-secret part, the part that's shared. How do I do that in practice? Okay, it's nice to say that I have this, this sort of conservation of entropy between the two. But how do I do that? How do I do that in practice? Well, let's go to something very, very simple. Let me look at doing a random linear code, and this gets back to network coding that Niels mentioned. Let me look at doing a random linear code of whatever data you have. So for instance, we have a packet payload. What does it mean for me to do a random linear coding? Means that I'm looking at this packet payload as a vector over some field of my choice, say f sub 2 8, okay? And I'm going to encode it, which means that I'm going to take these vectors, I'm going to linearly combine them, and I'm going to choose the coefficients of this linear combination uniformly, randomly, or whatever field I have to do. That's it. And with high probability, my field is large enough, by the way, if it's binary, likelihood of being involved is very high. But if my field is large enough, and my large enough means 2 to the 8, I take the 8, turn on sign, and infinity, that's fine, maybe big enough, then the likelihood, if these coefficients are chosen uniformly, randomly, independently, that this system of equations can be inverted is very high. And that likelihood is very high. Okay. So at this point, the reason is for doing this is now I have a lot more versatility. Right? I can really represent my initial data in whatever way I want. And one of the things it allows me to do, particularly if I'm looking at distributed systems, I mentioned at the beginning that I was going to try to link back to that, is that the issue of the coupon collector problem particularly goes away. So suppose that I'm doing a download. Let me give you a concrete example. Suppose that I'm doing a download where I have here, say, 4 servers. I mean, four servers and 4 clouds. And the way that I'm going to use these 4 clouds is I am going to randomly code everything that I have, and I'm going to distribute those randomly coded pieces among those 4 clouds. Now, why might I wish to do that? Well, obviously becomes nice and fast and furious. Count starts quickly, but then it's very slow. Okay? And count is kind of really sad, but you know, still something. And basically what happens is, remember that what I was doing was collecting different equations. Once I have enough equations with my memory coding, I have bingo, I decode, and that's what that line shows, or I receive enough. And the reason I want to do this is because it gives me a speed up. So this is with the full clouds I showed you before. Let's assume here I have 5 clouds. What you can see here is this is the time until you complete. So you see the mean, and you see the error bars. Okay? This is with replication, this is with random coding. So suppose in this case, what I have is I needed 32 pieces. So the initial file was 32 pieces long. Okay? That copy every file over on each and every of the 5 clouds, each of the whole 32 pieces. The minimum number in order to have everyone hold the same amount is 7. Right? That's fine. So, you know, 5 times 7 is 35 and smaller. But you can see that the coding gives you a big advantage both in terms of average behavior, but also in terms of reliability vis-a-vis duplication. Even having a little bit of coding is much better than replicating everything at every cloud. And it also gets rid of the difficulty of the proof I'm coming from. So suppose I have 2 clouds, and I'm downloading, and I don't know accurately how quickly these clouds are coming. Remember, I can see all that variability. That variability is not something that is easily measurable. It changes very quickly, not just with geography, but with time, and therefore an idea that I'm going to schedule a process is attractive, but impractical. So if I only had 2 clouds, I would start at the end of the file on one cloud, and at the other end of the file on the other cloud, until the 2 meet, kind of like, you know, doing the railroad thing. When I have 5 clouds, you know, you have one at one end, one at the other, 3 in the middle, and you're sort of awkwardly trying to get them to meet in a way that you don't end up, you know, with too many points. It becomes very creative. But the reason originally for distributing this information among the clouds was in effect this performance. Okay. Now the question, which is maybe an ancillary question, but which gets back to our question is, what is that doing in terms of the kind of fundamental trade-off that I showed you between that which is hidden and that which is not hidden? So in particular, what this is allowing you to do is potentially being able to do trusted storage over untrusted networks. And again, I'll harken back to this morning's session on overlay networks, because it's particularly interesting to hear some of the architectures which are very much concerned with privacy. And it says that a thing on a file, split into pieces, I encode it. I spread my encoded pieces over the different clouds. So for instance, I have here 6 pieces originally. I get 8 encoded pieces. I put 2 per cloud. I need to access 3 clouds at least in order to be able to decode. And if I'm only able to access 2 clouds, so here's that's the source of the top. Here's a sync node. Here's a terminal node, a legitimate terminal node. Here's an illegitimate node, eavesdropper. If the eavesdropper only has access to a subcritical number of clouds, he's not able to recover. And the amount of secret that is in effect generated this corresponds to the 2 pieces that he's missing. Okay? And it turns out that that optimal trade-off, remember that symbol secrecy, where I didn't explain to you clearly what that spreading out is. Okay, but again, intuitively you can imagine. You're just making sure that there is no similarity among the elements in the pre-image. There's no identifiable similarity. So you're not giving away anything. That is achieved for any maximum distance separable code. Okay? And in particular, with very high probability, the random code that I showed you is maximum distance separable. Probably that very quickly goes to work. So basically what happens is you have a code Solomon. The only problem is that you cannot recode it, so it becomes static, but that's a separate issue. And I have one of the pieces which is given to everybody, this S. I have one of the pieces which is maintained secret, whether it's maintained secret because there's a separate channel, like in the original setup where Alice and Bob had a K, separate channel, or it's maintained secret because it's a cloud that I trust is not going to be accessed, but I'm protected differently from the other clouds, or however it is that I got to it. Then what's going to happen is that the receiver, armed with what's a linear code, so this H is a linear transformation on the original X, and another linear code G, concatenating the two codes and inverting them is able to recover the X. So in this case, the secret key, the C of K, is this GXM. It's basically what came out of encoding the original data with a particular matrix which shrunk it. So think of that data as being, in effect, over the clouds that I consider are not going to be affected. By the way, in the setup that I showed you here, I don't necessarily know which clouds are not going to be affected, right? I didn't necessarily say that it's the third cloud that's safe. Okay. And the theorem is the following, that if the source is uniform, identically distributed, this thing achieves optimal absolute secrecy. It's on that. So I can use a random code, I can use a Solomon code, you can pick your favorite coding book, and I can sell it, open it, pick an NMR matrix, slap it on there, it works. That's it. It's this optimum bucketing, spreading the randomness between the information and the secret. So at this point, you get really happy. You got really happy. Because it said, look, there is a notion of secrecy which does link together, does form a continuum between keys such as I use right now generally, the one I had. By the way, it also forms a continuum with all other kinds of measures such as weak secrecy, etc., which relate particularly to information theoretic security literature that I mentioned from late in the last decade. Okay? So it does really unify that. It unifies all of those. And by the way, there is a trade-off, which is a fundamental trade-off, and I can get to it constructively. So at this point, like I said, you feel very smug. And so you see at this point, you look at this and say, okay, what could go wrong? All right? If then, all right, it's not the then, must be the if. If the source is uniform, ID, independent, identically distributed. Remember I talked about this memberless source, discrete source. Well, that's where it can go wrong. Because are things uniform? And what can I say about uniform? So, things, of course, are not uniform. And even if you go back to this issue of having, let's say, a standard key, one of the standard keys that we use is not necessarily a key that's generated by your crypto system. One of the standard keys that we use is a password. Right? So if you think of the list source coding, that's in effect what somebody is doing who's trying to break into your system. The person's going to go over every single possible password. In order to go over every possible single password, is then going to see whether he breaks in or not, whether he's able to decode what he had. Whatever the relation was between the password and the decode. Brute force attacks happen and happen a lot. So if you recall some months ago, there was all sorts of discussion and titillation on all those nudie pictures. They were, as far as we could tell, brute force attacks. Okay, it wasn't that people had been particularly silly or careless. They had password protected, what was private information, and some people broke into it. Okay? So the question then becomes, well, what about this uniform? to what I said at the beginning of the talk, what about entropy, which is generally the way that you get around to define the uniform. So, passwords are clearly not uniform. Okay, so there are programs out there for password cracking, and you can look at passwords, and you can see these passwords were taken out of that Adobe leak that happened. And what happened in that case is that you had a ciphertext, and it was kept together with a hint, so you could see the hint. So the problem here, and by the way, you can see how non-uniform it is, because 1, 2, 3, 4, 5, 6. There were a lot of users for that. 1, 2, 3, 4, 5, 6, 7, 8. That was also good. You can see the amazing hits. Okay? And what would happen in that case is that even if your password had a hint that wasn't quite as transparent as those hints, if you happen to share the password with somebody who was maybe less subtle in the choice of his or her hint, you have a problem. Okay? So, there's somebody there who didn't add their security question, they just had their office phone, but they had their email, so that was very hard for somebody to pick it up. But just to give you an idea here of what pops up, you had the questions such as, furry little bugger, and Tasha, and animal, and bunny, and that's that. So, hop hop, if at this point you don't know what it is, you really have an issue. Now, Tasha wasn't bad, because what are the chances somebody would know that your rabbit is called Tasha? But, the problem is you ended up sharing, of course, everything was hashed the same, there was a single key, so you end up sharing the password with somebody who put hop hop, and somebody quickly guesses bunny. So basically what happens is, it's not uniform, even if you thought it was uniform, the non-uniformity comes, either because somebody chose the password in a non-uniform fashion, or because there was some side information that gave the likelihood of the passwords, because the attacker asked as a password bunny, and the system says this. And the question is that, remember that what we're saying is that what's on some protected or somehow not reachable cloud is my password. The fact that it came from my own data, the fact that I'm self-keying, that's neither here nor there. At least if everything was uniform, we're self-keying in an optimal way. And this is what happens. So, turns out that regular entropy, Shannon entropy, which I mentioned before, which I'll give you the definition of in a bit, is not a real determinant. This was known from Massey and Aragon in the 90s. The other thing which was recently found out, presented in 2013, this is what conducted this student Mark Christensen, is that using compression is the same way to give you the right randomization. And this goes back to the issue I mentioned before about, and you'll see that in a picture very quickly, about this idea that information theoretic security, which relies on certain assumptions, which primary among those assumptions is the fact that you have this uniform ID source. Itself hangs its hat on the fact that you've done source coding, that you've done compression, that in order to have a very efficient representation of the data, you compressed your data to the point where its entropy is close to the entropy of a uniform source. Because otherwise you would have more space to compress. Okay? And it turns out that even though that's true in terms of Shannon entropy, it's actually not enough in terms of the kinds of entropy that we need to look at. Another thing I'll talk briefly about is that hiding the statistics does not help much. And that's weird and discouraging, right? Because when I showed you that table, and we all feel very smug, it's like, well, of course, if you choose 1, 2, 3, 4, 5, 6, duh. But of course, the idea there is that you know the statistics, and that somehow if somebody didn't know the statistics, it would be harder. But it turns out it's not so much the knowledge of the statistics, it's the lack of uniformity that's important. Okay, so at this point, we're going to ask, what's entropy? It's a cute little cartoon. But the idea here is that, entropy is not about Shannon. And we're not the only ones to talk about Shannon entropy. This has been updated since by NIST. But NIST does give you minimum number of bits per security. But these recommendations assume truly random bits. So for instance, when they say this is the number of bits you need, and by the way, you look at these recommendations, these are recommendations that are sometimes going, pretty far in the future. I mean, we're talking about things here that are supposed to hold you in good stead until 2020. Right. So, should I really look at the number of bits in terms of, this is my bit representation of whatever student I have. If I'm using bits with Shannon entropy rate of 0.1, should I use 2,000 bits instead of 200? What's going on? And what does it mean if I'm not truly random? Should I just be mapping Shannon entropy? Okay, so some of the prior work in this area was basically mostly, first of all, relating gas work to Shannon entropy, relating Massey to that in 94. Aricon, many of you may know more from polar codes, maybe one of the things you're supposed to know. Famous, however, Aricon came along and showed what the average gas work was for IEEE sources. Interestingly, it was not looking at gas work for the kind of password cracking that we're thinking about. It was actually looking at it for convolutional inquiry. Okay, came from a completely different arena. There were extensions to Markov sources, again, distortion and so on. And then the work that we're going to be using, because it allows us to go away from averages and look at specific lengths, not just asymptotic results, but specific lengths, is the work by Mark Richardson and Duffy that appeared in my T-Transactions in 2013. Okay, so I told you that the parameters of the source don't matter that much. What does that mean? So if you hung out at some point in information theory classes and was really familiar, if you didn't, that's okay because, this is pretty much all you need to know for the purposes of this talk. Generally, we tend to parameterize sources. So we have a parametric probability measure, mu is not the same mu as before. It's only a measure on the screen. X is still the source alphabet. And then I have some parameters which tell me basically in a class of different distributions, which of those distributions I'm picking. So just to give you some idea, that's going to determine optimal guessing. So for instance, I'm going to call G the guessing order. I always start guessing from the most likely to the least likely. So for instance, if I was over here, obviously the first thing I'm going to guess is the one at the top, the frequent one, followed by the second one, and so on. Right? You need to come to that to this stuff to be validated. And we're going to look at different parameter vectors. So for instance, suppose that I have this alphabet guessing order. Suppose that I have a binary regular source where my probability of A is 0.8 and my probability of B therefore is 0.2. I would start out by guessing the all A's, and followed by anything that has 2 A's, and followed by anything that's 1 A, and then followed by the one that has something like that. Okay? Whereas, of course, if I have a uniform distribution, then they all have the same probability. It doesn't matter how I do. All right, so entropy. I've been promising that I'm going to show you this. By the way, this is the fastest thing I'll show you. Except for lunch. I shouldn't show you too much. So basically, Shannon entropy, as I told you, is this sum of minus p log p, or p log 1 to p. Okay? That's Shannon entropy. Same entropy that we hung out with. Rayleigh entropy is something very similar, and it has this parameter alpha. And if I take this alpha to go to 1, which of course I can't quite because I can't divide by 0, but if I take the limit of this thing as alpha goes to 1, I get that. So for the purposes of the discussion, let's just say that H, which is the Shannon entropy, is the Rayleigh entropy with parameter 1. Even though it's not quite because it's alright? So why would I want to hang out in Rayleigh entropy? Well, people use Rayleigh entropy for all sorts of things, image processing and so on and so forth. But what I showed in 96 is that if I look at the expected number of guesses normalized by the length of my string, it doesn't get to the entropy sub 1, the entropy that we assume we know, the Shannon entropy, it gets the Ranye entropy of order 1/2. Okay? And if we define something which we call inscrutability, which we recently did also with Mark and then Bob Holloway and Karami, and you look at the first symbol of inscrutability, basically, if you look at something a little different than what Aragon looked at, as opposed to looking at this expected value of the guesswork, you look at this log of the expectation. So that means that you're looking at the contribution rate of an extra symbol to the exponent. And you can see how that relates to what we did at the beginning. Right? I'm looking at the incremental gain from one bit, one symbol. Remember what I was doing before is sloshing the symbols back and forth between the secret part and the non-secret part. Right? So I'm looking now, if I add one more symbol, how much does that complicate the attacker's job? It's an incremental gain to thwarting the attacker. So this is what you can see in this difference between Shannon entropy and Ranye entropy, which is coming in this inscrutability. I told you I'd show you a picture. Where you can see our inscrutability rate is there, it's the ordinate. The abscissa is the parameter theta, so for instance, the binary is between being completely deterministic and 0 or 1, uniform is at 5. Okay? So this is and the ordinate are. This difference translates into an exponential number of extra guesses. And in particular, if I take information theoretic approaches to compression, things like asymptotic partition problem-based system, which, like I said, have always underlined the assumption that the basic assumption that the source is uniform. Because I've already compressed it, I got to that uniform entropy. Right? I got to that top over there. Or very close. What happens is that gap between getting to the top here in blue and getting to the top in the red corresponds to an asymptotic difference in the number of guesses. So I'm overestimating my number of guesses that the attacker has to take over what he really has to take. And I'm overestimating in a way which is diverging exponentially with the length of my key. That's not good. Okay? So I'm off by assuming that it's the Shannon entropy versus the Ranye entropy of order 1/2. I'm off by something which goes very, very quickly. So as long as I'm not exactly uniform, which I never am, I'm getting towards uniform. I'm off in a way which I didn't realize necessarily was hurting me. So yes, I was maybe converging very quickly in Shannon, but not enough in Ranye. Okay. So going back to the end, to this idea of multiple cloud systems, remember what I said is, I want to know if I spread things over these different clouds, and I knew what happened if the source was an ID, but now, if it's not an ID source, I want to know, how can I quantify the security of that? Because I'm no longer on that line. That line assumed that I had a uniform source, that perfect trade-off in where I put my bits, which, by the way, I think still tells you a lot. But if I just sat there and I told you, uniform bits are a problem, that's what we get from compression, I'd be lying to you because of that gap in those two curves. So then what happens is I just need to break into enough clouds. So remember the picture I showed you where, I had overall I needed 6 pieces. I had 2 pieces per cloud. So if I got any 3 out of the 4 clouds, I was done. Right? As an attack. Remember that? So basically what I need to do is I'm going to try to break in any 3 clouds, and then I'll be done. That means that I need to guess U out of the password, so 3 out of 4 in the example that I gave. So, what happens in that case? Well, what happens is it becomes complicated. Because as we're guessing these strings, we may start out with, 1 cloud other users for maybe even more highly perform, right? And the order in which you would guess actually changes according to the previous guesses. Now, what didn't happen with guesswork when I had a single system, right? A distribution from more likely to be slightly guess or slightly work my way down in decreasing order of likelihood. That's the only reasonable thing to do. Now, it's more complicated because I have these vectors. But the thing that comes out of this is the following. The relevant quantity is a range entropy order u v minus u plus 1 over v minus u plus 2. Now, bear with me for a second. When I only had to guess 1 out of 1 passwords, this is what happened. So that's good. That's what we were working for. What happens when v becomes very large? I have lots and lots and lots of clouds. What is this going to? Yes, it's fun. Which is channel entropy. Right? Remember I told you channel entropy was not the right thing, but somehow, if you have lots and lots and lots of clouds, you're getting back to a channel entropy, right? But the other thing that's interesting, and this gets back to this characterization that Martin Ken gave away from the mean, is that it's no longer the case that I just have a worst case cloud. I don't have my weakest link among all my clouds. If I look at the range function in terms of the rate of the guesswork, okay, with time, so this is a year's time, what's going to happen is suppose that one of them is uniform, so it's straight. Every time I'm just decreasing by 1. And the other one is I given non-uniform. It could be that one of the clouds is originally my most vulnerable cloud, and as I make more guesses, another cloud. So maybe the cloud that had the non-uniform was more vulnerable because it was more likely to the password maybe that a user used. It's more likely that I will guess it. But pretty much with passwords, either I guess it at the beginning or else I have a long tail. I'm in for the long haul. So at that point, it may be the uniform, shorter key that becomes my problem. So it's not necessarily that one is better than the other, and therefore the security of your system doesn't just depend on one cloud, it depends on the combination of elements. Okay, so just to conclude, presented at least a sort of different definition of information theoretic security, which, as I said, combines, unifies one-time path, finite length key, weak secrecy, etc., and showed you very straightforward codes that can achieve the trade-off that outcome. But it is predicated on having some source uniformity assumptions. And what I hope I convinced you is that these source uniformity assumptions are very, very tricky. We're not just now starting to get really a handle on what that means, and that maybe the real approach to that is not so much entropy in the Shannon sense, even that that's what we try to start at the top with, the one-time path which that attribute into Y and into K. Okay? But really, linear entropy of different orders. Okay, so you can imagine there's lots of work. We're going to see how to increase guesswork, other guesswork, key like equivalences. What are the distribution sources after source coding? The definite uniform. What is linear entropy of common password files? Alan Arami, a postdoc, has been working with students over the summer, just looking at lots and lots of password files and trying to compare this criteria to linear entropy. What does it look like? What do we get? And then sort of interesting questions that come out of this. So, can we use simple linear mixtures to approach uniformity? Right? If I use a random linear network code like I did at the beginning, the random linear network code maintains uniformity, and it tends to uniform. But does it tend to move fast enough in terms of these kinds of linear entropies? Should I be resurrecting codes
Thank you very much for this very fascinating talk. I have maybe a provocative question.
Oh, please.
So I'm voting for killing the password. Why do you want to prolong the life of the password? Shouldn't we use more security mechanisms? And maybe as a follow-up, it's like, can this be used for something else?
So that's a good question. So the password here is basically the secret that I'm trying to guess, right? And certainly, what all I was pointing out here is that what that secret was could be a key, right? It could be a self-keyed data, which came, as I said, when we were doing this multiple cloud. If I'm, suppose I'm the attacker and I'm missing those two pieces, those two chunks. How much work is it going to be for me to guess it, right? That's one of the questions. So I think, and the other question is, if I'm going to be putting things over different clouds, maybe some of them don't have passwords and some of them do. Is it the case that it's always, one of them is the weakest link?
Yeah.
Exactly. And what was interesting is that it's not. It varies with time. As time goes on and more guesses were done, one of them may become the weaker link over the other. That's also, I think that's sort of unexpected, right? You sort of intuitively say, okay, this is the weaker of the class. But maybe it's a weaker one at the beginning, but not at the end. Maybe that's the one that's actually saving at the end. And that was unexpected. And you have to sort of very context-dependent security when you start distributing among these other clouds.
Yeah, that's true. Thank you very much.
Yeah.
Yeah, thanks for the very interesting talk. This is all great, amazing stuff. I just have a question. How do you actually build practical protocols using some of these ideas that would work over the internet?
That's a very good question. I think it depends very much on which aspects you're looking at. I mean, certainly the multi-cloud aspect, that I showed you, that was built. That's commercially available. Even though, as I mentioned, the original impetus was performance. You can see the performance benefits there. So we're starting to understand more of the side benefits in terms of security. That's being done at the application level. So, you store your, you have an application level distribution of content and recovery. Right? That was the most straightforward. So that's my main answer. The other answers I think are excellent. And frankly, I don't know. The other question I think is excellent. The answer to that is very interesting. In terms of looking at more transport level, and if you do things for application, I just give you an example. I think that would be fascinating. I mean, certainly we've been looking at doing multiple path transport using coding with multiple path. That's still from a single source. So the next question is, how do you do multi-source? Could you do multi-source? Could you do multi-source? It's very interesting. In terms of where this goes with the guesswork, I don't know. I don't know exactly what it means. This goes back to the other question. It's an intriguing remark based on recent results, but I don't know exactly where it takes us, other than to at least reconsider some of those aspects.
Yes, in your context, how can we use in your context, how can we use biometric information to improve the efficiency of password representations?
That's a good question. I don't know much about biometric information. It would be, in the context here, it would be a key upstream, right? Exactly how that key would do relative to, say, taking the file, source coding it, taking, then randomly in our coding, taking a piece of it and putting it aside, I don't know. Right. Because both the, for instance, if you ask me, what's the ranking entropy of biometric information? Good question. If you know about biometric information, maybe you can count, right? I mean, we're just trying to figure out what the entropies, ranking entropies are for known, data no files with leaked passwords. So that's a good question, but I think the answer is, I don't know, but there has to be, but at least this gives you some idea of metrics that you might be able to use.
That was the question.
Yeah, hi. You have mentioned about this distribution of sources. I was just wondering that what would be the impact of it using single sign-on techniques, where we are moving towards single sign-on for all these distributed clouds. So would it do you think when we distribute the sources, would it impact the single sign-on techniques as well?
That's a good question. I don't know. Relative to this, it's a little orthogonal, right? In the sense that I was distributing, relative to this, it's somewhat orthogonal, I think, unless there's something that I'm missing. Because, as I said, in the application layer, I can just hide it.
But there's another aspect in which the community is moving towards single sign-on techniques to.
Yeah. So in the application approach that I showed you, I'm just basically hiding it. I don't think they're incompatible. Right. It looks to me like it's orthogonal, but I would have to think of whether something's hiding there. But a priori, I would imagine that it's orthogonal, but it would require more thought. Yes, so that's a good question.
I think we have time for one last question.
Thank you.
We're not done yet.